welcome to the second part of the STAB57 final review seminar for winter 2025. My name is Kevin, and I will be going over Bayesian inference and regression in particular. So to begin, the Bayesian interpretation of probability is that it is subjective and it is a measure of belief given evidence. Typically for the frequentist interpretation, we have our evidence and we have a model that doesn't really change. However, for the Bayesian interpretation, we are given some prior belief and we may update this belief based off of the new evidence that we obtain from sampling some distribution. And we may be able, in this case, we may update our model or its parameters associated with it. To begin with, Bayesian inference follows as a result of the Bayes rule. So if you remember from STAB52, Bayes rule is as follows. Probability of A given B is equal to the probability of B given A, probability of A over probability of B. And we are able to translate this one in terms of samples by letting H be some statistical hypothesis, such as maybe we have a null hypothesis as well as an alternative hypothesis. We let I be some sort of prior knowledge or intuition or some prior evidence perhaps, and we let D be the data that we obtain from repeatedly sampling a distribution. Then the probability of H given the intuition and the data is equal to the probability of the data occurring given this hypothesis and intuition times the probability of this hypothesis given the intuition over probability of this data occurring given our prior intuition. So probability of HI in this case will be considered the prior, and the probability of H given I and our new data is the posterior. So this translates quite well from what we know of as the Bayes rule. So the probability of H being equal to some hypothesis H given I, D can be expressed as a random variable of the form pi theta given S, with pi theta without the sample being the prior distribution and F theta S being what we know of as the likelihood of obtaining the sample given some parameter theta, where theta can be maybe a single parameter like mu or multiple parameters like mu sigma squared. So the probability of data given information is equal to MS is simply a normalization constant to ensure that this pi theta given S is a valid distribution. At the end of the day, if we wanted this excluded, we are able to, as at the end of the day, the proportion of pi theta and F theta S over MS is proportional to just pi theta and F theta S. So this MS value ends up, we are actually allowed to ignore it as long as the final distribution has a total CDF of 1. So given that S is typically pulled from a random sample, naturally we can use the random sample formula, which is F theta S is equal to the product from I is equal to 1 to n of F of xi given theta, where xi is every individual sample. So, given a posterior distribution, it is possible to make the same inferences as the ones used in classical statistics. So like the maximum likelihood estimate, as well as establishing like confidence intervals. In this case, they're called credible intervals, as well as, maybe using like maximum a posteriori estimation. For a parameter theta, it is possible to establish a credible interval using the same process as establishing a confidence interval, given our posterior belief of theta. As with confidence intervals, it is in our best interest to make this region as small as possible. Typically for symmetric distributions like the normal distribution, this will be centered about the mean. Maybe for like a different kind of distribution, maybe for like for exponential distribution, it may be starting from 0. The best possible estimate of theta is called the posterior mode. And this is the ideal estimate. So instead of establishing a confidence interval, if we wanted to pick just one answer, we would pick theta hat, which is equal to the mode of theta, which is equal to max of theta. In a continuous distribution, this can be obtained by maximizing the likelihood of pi theta given S using maximum likelihood estimates. Choosing a prior distribution. A family of priors pi lambda, where lambda is in big lambda, which is a sort of a collection of possible priors, for parameter theta is a conjugate prior if for all data S and lambda priors, the posterior distribution is in the same family, i.e. the pi lambda of whatever information given S is still in the same family as pi lambda. So essentially, for example, if we have like a gamma distribution as the prior, if the posterior is also gamma. Perhaps the parameter values itself, as in like theta, may change, but at the end of the day, the underlying distribution is still the same. This is what we call conjugate prior. Also, sometimes a statistician may not favor any particular prior. For example, if we don't have any evidence regarding whatever we are sampling, we may choose a non-informative prior. Typically, this one would be a uniform distribution over the parameter space. For example, given theta is given we have a finite number of possible, if we have like a finite number of possible parameters, we choose pi theta I to be 1 over n. So every single one of these parameters are equally likely. This really only works if we have a finite number of possible parameters to choose from. We can choose pi theta I to be 1 over n. So pi theta is distributed uniformly. Or for example, we may use something called the Jeffreys prior, which is where the prior is proportional to the square root of the determinant of the information, of the Fisher information. In this way, sort of like the prior, sort of like the posterior will sort of scale with the prior. Sometimes the prior may not even be a proper distribution. This is what we call an improper prior. However, improper priors may still lead to proper posteriors. For example, this occurs when the integral of the prior diverges, i.e. the integral over the prior space of the prior d theta is equal to infinity. So the prior is not a proper probability distribution. This may still lead to a proper posterior distribution, so a finite posterior distribution. Okay, so now we will have a question. Suppose x1, x2, all the way up to xn is IID Poisson, where theta and where lambda is believed to come from a gamma with alpha naught and beta naught as its parameters distribution. Find the posterior distribution of lambda. Find the posterior mean and variance of this lambda. Using a non-informative prior, find the posterior mode. Okay, so if you wish to, you feel free to pause the video and try the question on your own before I give the answer. So, to start with, we are given that x1 is distributed Poisson, where lambda can be expressed in terms of a gamma distribution. So to start with, let's write out the Poisson distribution. So the Poisson distribution is as follows. So f(x) is equal to e to the negative lambda x over x factorial. So the likelihood of our sample being equal to, let's say we have a sample that we obtain. Now, given our any lambda, given any lambda is, we can just use the definition of likelihood as follows: is equal to the product from 1 to n of, where n is the sample size of e to the negative lambda to the x I over xi factorial, where xi is from the sample, where s is equal to xi, where I is equal to 1 all the way up to n. Now let's go and factor this a little bit. We can bring this one out, right? And since this is lambda to the xi, this product will turn into a sum when it's moved from here to here. So let's do that as well. Equal to e to the negative lambda times lambda to the sum of xi, for xi is from 1 to n, over, I can just keep that over here. Let's have it as j is equal to 1 and x j factorial. Okay, so the posterior distribution will be as follows. So pi of lambda given s is proportional to f of theta s, f of lambda, in this case, we can lambda s, pi of lambda. So in this case, pi of lambda is gamma, right? So we have the gamma distribution, which is, we have beta naught to alpha naught over gamma of alpha naught times the lambda of alpha naught minus 1 e to the negative beta naught lambda. So this is what we have as the prior distribution, which is just a gamma distribution with alpha naught and beta naught as its parameters. So this one is equal to this one, e to the negative lambda to the sum xi over product xj, or j is the 1 to n factorial dot this one over here. So b naught, a naught, gamma alpha naught, lambda a one b2 b naught 1. So this one is proportional to what we have. It's this one is, we can have this, this gamma naught is sort of irrelevant. We can just sort of get rid of terms which we can sort of group together like terms. For example, we have this one and this one are alike, and we have this one and this one are alike. Since it's a multiplication, we can just we can just add them together. These two are constant terms, so we can get rid of that one. And we can also get rid of this one because this one's just a big constant term. So this one is proportional to e to the negative lambda, and then times n. I forgot to do negative. E to the n plus beta naught lambda with the sum of xi plus alpha naught minus 1. And what do you know? This is sort of in the structure of a gamma distribution. We don't have any of the terms here, but that shouldn't really matter because it still follows, like the structure still follows a gamma distribution. Therefore, you can say that pi of theta given s is distributed gamma with parameters, and these are our new alpha naughts and beta naughts. So we have parameters sum of xi from I is equal to 1 all the way up to n plus alpha naught. So this one should be alpha naught over here. So this is alpha naught minus 1, the new alpha naught minus 1. And n plus beta naught. So this one is minus lambda times, this is our new beta naught. So we can say that alpha naught is, the new alpha naught is equal to sum of xi plus our old alpha naught, and the new beta naught is equal to n plus beta naught, our original beta naught. Okay, so second question. Find the posterior mean and variance of lambda. So first, we take the first and second moments of the gamma distribution. We can take the first moment, so mu is equal to alpha over beta, and then we take the second central moment, which is sigma squared, is equal to alpha over beta naught. So the posterior mean is, mu hat, which is equal to alpha naught hat over alpha beta naught hat. Now this one is equal to, we have from before, alpha naught is equal to sum of xi plus alpha naught over our new beta, which is n plus beta naught. And then we take our posterior variance, so posterior variance is sigma square hat is equal to alpha naught hat over beta naught hat squared, which is equal to same thing as before, sigma xi over alpha naught over n plus beta naught, and then this one be squared. Finally, using a non-informative prior, find the posterior mode. So under a non-informative prior, we do not have any favors toward any particular value of lambda. So the posterior mode instead depends solely on the information obtained by sampling. The posterior mode is the maximum likelihood estimate of lambda. And the MLE of this lambda, so the MLE of lambda is lambda hat is equal to the argmax of L of theta given S, where little l is the log likelihood. So this one is equal to arg max of log e to the negative n lambda to the power of xi over the product of xj factorial. This one is equal to our max of, we can just take out this as entirely. So this one is equal to arg max of a negative lambda. To move this one out, and then plus we can take this one out and then move this one. We move this one into the log. So this one is equal to sigma xi log lambda, and minus, this is the division at the bottom, minus from the sum from I is equal to 1 to n of log xj factorial. So we have a very long formula. However, if we are taking the argmax, we have to, and we also have, so we take the derivative of lambda with respect to this L. We take the derivative of this log likelihood function with respect to lambda, and this is how we maximize this lambda hat. So this one we can get rid of that one entirely, and then this one vanishes, is equal to, let's see, equal to this one. So this one becomes 1 over lambda, because lambda should be strictly greater than or equal to 0, times sigma xi minus, and then we have this n over here, this lambda gets removed, so this one becomes n. So we were left with 1 over lambda sum sigma xi minus n. So setting the derivative to 0, so we set the derivative to 0. So this one, so we have this one is equal to 0. We have 0 is equal to 1 over lambda hat sigma xi minus n. We have that n is equal to 1 over lambda hat sigma xi. And then we have, so then we have that means we have lambda hat equal to sigma xi over n. So therefore, we can say that the posterior mode is equal to x bar, which is equal to sigma xi over n. Now we will begin the second part of this recording, which is now we are going to change our focus to regression. So to begin with, what is relevant is correlation. So what is the correlation between two variables? So we can express this using, remember, the correlation formula, right? We have the covariance, we have a correlation of x and y is equal to the covariance of x, y over the standard deviation, x times the standard deviation of y. This is what we have as the correlation between x and y. To extend this one to samples, instead we take, we don't really know what the expected value of some distribution is, but if we sample it, we can get, so this one is, so we can get, remember that if we sample, we can get that the expected value of x is equal to x bar. We can get that the expected value of x bar is equal to x, the expected value of x. When we sample two different variables, remember that we can get this one and the sample variance, if you can recall, is equal to the sample variance over here. So the correlation coefficient is as follows. Sum of xi minus x bar times yi minus y bar is over the square root of the sum of xi minus x bar square root of yi minus y bar square. And then we have to remember that the bottom part over here will always be greater than the top, or greater than or equal to the top. So the correlation will always be bounded below by -1 and above by 1. So -1 that will be less than or equal to r, which is less than or equal to 1. So the absolute value of r is equal to 1 indicates that the correlation is equal to the standard deviation of x times the covariance is equal to the standard deviation of x times the standard deviation of y, which indicates a perfect correlation. So this one should be similar to knowledge from STAB57, but this time we are applying it to samples. So instead of mean, we use sample means, and instead of variance, we use sample variance. So the goal of regression is we have a set of data points, and for simple linear regression, which is what we are doing in this case, we have our independent variable, in this case is TV, and in this case, our dependent variable is sales, and we want to try to find some sort of line which best fits through all of these data points. So this regression line will obviously take the form of y equals mx plus b, as all lines do in two-dimensional space. we get this regression line is equal to y hat, which is our fitted line, which is our predicted value. This is predicted value, is equal to beta 2x plus beta 1. Okay, so this one is equivalent to the y-intercept, as with y equals mx plus b, and this one over here is the slope of the line. So next, we will define a measurement to see how good this line fits. For example, we have over here, we have a graph. We can take the distance, the minimum distance from this point to this line, or in this case, we are actually taking the vertical distance from this point to this line. And we can take the vertical distance from this line, this point to this line. We can square it. So this one, instead, we square it. So the distances become positive, and then we sum them all together, and this one will give us a estimation to how good or bad our line will fit the data. In this case, the square error is as follows: yi minus y hat I squared. Sum them all together, which is equivalently equal to yi minus b1 minus b2 xi squared. Then we sum them all together, and this gives us our squared error. So the goal of least squares is to minimize this error, and in minimizing this error, we will maximize our fit of this data. So we can do that obviously by taking the derivative with respect to parameter b1 and b2. So in this case, we take the derivative of this, we get -2 sum times the sum of yi minus b1 minus b2 xi. Obviously, we want to minimize it, so we take it to 0. We know that this function over here is convex. So, maybe we can use like some sort of like gradient descent, or we can just take out the plain old derivative. Either way, we should come up to a single closed form solution of the following form. B1 is equal to yi hat minus b2 x hat. And then B2 will have the following formula, where sum of xi minus x bar, yi minus y bar over sum of xi minus x bar squared, alternatively is equal to sum of xi yi minus nx bar y bar, nx bar times y bar over the sum of xi squared minus nx bar squared. Alternative, you may see me write this one as the sum of squares of x and y over the sum of square of x and x. So the sum of square of x and y is we have x over here and y over here, and the sum of square of x over here and x over here again. So this is how I also may write this value. So in terms of simple linear regression, we assume that yi given x equals xi should be IID normal with beta 1 plus beta 2 xi and sigma squared. So if we have our answer so alternatively, you may also see it as written as yi is equal to beta 1 plus beta 2 xi plus epsilon, where epsilon is sort of the error. And then this error will be distributed normal, 0, sigma squared. These are equivalent representations, right? Since this one is just this one, but centered at mean 0. To find the best possible line of fit, we can use maximum likelihood estimator method to find the best possible estimators. So the likelihood function is defined as follows: L of beta 1, beta 2, sigma squared is equal to this, which is equal to all of this, blah, 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 blah. Either way is that from this likelihood function, we will all, which this likelihood function is, if we were to minimize it, we would get the same following results. So we arrived at the same conclusion. Now, even using like this different, like this likelihood representation, we will still arrive at the same closed form solution of B1 is equal to yi bar minus B2x bar, and B2 is equal to S sum of squares of x and y over sum of squares of x and x. Okay, since we have this, we can infer that B1 is distributed normal, where the expected value is beta 1, which is the true underlying. So this one over here is what we consider our estimate. So our estimate of beta 1 should be distributed normal, where this is the true value, the expected value is the true value of beta 1 if the data were to come from a linear relationship. You can say that this one is the true value beta 1, and then times, and then the variance is sigma squared of 1 over n plus x squared, x bar squared minus the sum of squares of x and x. So sigma of xi minus x bar squared. That beta 2, or B2 in this case, is distributed normal with beta 2 as the true value, as what we expect, and then we have the variance of sigma square over sigma of x, sum of xi minus x bar squared. So a confidence interval we can use the following values from above, right? We can use the confidence interval methods that you should have, that you may have learned earlier, where we take the z, where we take the standard normal, and then where this one is equal to the standard error. So this one is equal to standard error, and since we have that B2 is distributed normal of beta 2 and sigma squared over sigma of xi minus x bar squared. We can use this idea that it is distributed normal and just sort of apply it here. So B2, since B2, the expected value of B2 is beta 2, we can just take B2 plus or minus this z of the z score of this standard error over here. What is sigma squared? We don't know what sigma squared is. No, typically we're not provided what sigma squared is. So it is an unknown population parameter, so how can we use it? So instead, we use the estimated value of sigma of yi minus yi hat squared. So this one is essentially equal to the mean square error. Instead, we take 1 over n minus 2 degrees of freedom, since we have yi hat consists of beta 1, consists of, let me see, b1 plus b2x. So we have two fixed values, so if we fix two of them, we have n minus 2 degrees of freedom. When we sum them all together, we have n, and then we have two fixed values, so n minus 2 degrees of freedom for s squared. So instead, we have a sample variance. So in this case, we use a t distribution instead. So now it will look something like this. B2 is sort of distributed with centered around 0. Since the expected value is beta 2, and then we have plus or minus t with n minus 2 degrees of freedom times the square root of s squared over the sum of squares of x and x. So the next part is sort of some particularly applications of regression, especially towards detecting lines of best fit and whether or not they exist. This is called ANOVA, or analysis of variance. So in this case, under analysis of variance, It states that the total sum of squares should be equal to the regression sum of squares plus error sum of squares. Since we could decompose this total sum of squares, yi minus y bar into yi minus y hat I and y hat I minus y bar squared. So as such, we could decompose this total sum of squares into regression sum of squares and error sum of squares. So regression sum of squares explains the residuals, that the amount of residual that can be explained through regression, and error sum of square is the amount of residuals that cannot be explained, that can sort of be explained only by factors outside of regression. Typically, this is just random like variance, since from before we have that errors should be distributed normal 0 sigma squared. So this error sum of squares should represent this residuals over here. So total sum of squares is just the sum from yi minus y bar squared. And the regression sum of squares is our best fit of y hat I minus y bar squared, and the error sum of squares is equal to yi minus y hat I squared, which is the residuals, the sum of squares of all the residuals. Next, the coefficient of determination is defined as follows. R squared is equal to RSS over TSS. So R squared is equal to regression sum of squares over the over the total sum of squares. And this will explain how much our regression model is explaining. Okay, so higher values indicates that we have a very good model, and the model fits very well with very small error sum of squares in comparison. So when the regression sum of squares is approximately equal to the total sum of squares, we have that the R squared value is very close to 1. Is approximately 1. So we have to remember that regression sum of squares is bounded below by 0 and bounded above by 1. This is because regression sum of squares, remember that we squared these errors, so this one will become positive no matter what. And the total sum of squares, this is also squared, so it will always be positive. So this one represents so in simple linear regression, we can have that the correlation is equal to this coefficient of determination. In multiple, and if we have multiple regressions, if we have multiple linear regression, this may be referred to like multiple R squared and adjusted R squared. It may be different depending on how many degrees of freedom and how many variables you have. So however, in simple linear regression with only one feature, we have to remember that we only have one explanatory variable, so we have the same degrees of freedom all around the board. Next, we will talk about regression with categorical variables. Let's say we want to apply regression on height with respect to some biological sex, such as male or female. Our independent variable is now xf, where 0, which is an indicator variable, so xi, xf is an indicator for its distributed Bernoulli. So it's 0 if x is male and 1 if x is female. So now our regression formula will look as follows. Y hat I is equal to b1 plus b2 xf, where xf can only take values from 0 to 1. So under our assumption that y given x of x f is equal to x of f is distributed normal with beta 1 plus beta 2 xf and sigma square variance. How can this be interpreted now? It is no longer a slope, but instead we have b1 is equal to mu m, and this is the average of how tall a male would be, and b2 is equal to mu of f minus mu of m, which is the average difference between the male and the female. So in this case, You may also see this with this sort of representation of x1 as a dummy variable. You may also see it being called as so-called one hot encoding. This is especially in context of like machine learning. They typically call it one hot encoding. So for every regression model with categorical variables, there is a base category. The rest of the category is represented using a binary indicator. Once again, this is our so-called one hot encoding. We have that y given b is equal to b, blah, 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 z is equal to z, xz is equal to xz, is distributed beta 1 plus beta 2 xb plus so and so on, plus beta n xz, and sigma squared. And once again, we can still have the same regression representation. However, we have beta 1 is the parameter value of our base category, and beta I is the difference in the value from b beta 1 to category I. So if we want to fit a model, we need n minus 1 different indicator dummy variables. Alternatively, you may see this one being called one-way, this analysis being called one-way ANOVA. Okay, so now on to the question. So given this summary of 5 observations below, so we have n is equal to 5, we have sigma xi is equal to 15, sigma yi is equal to 42, and sigma xi minus x bar squared is equal to 30, sigma y minus y bar squared is equal to 32, and the sum of squares between x and y is 25. Suppose we're trying to fit this following regression model, or alternatively, we have y is equal to beta 1 plus beta 2x plus epsilon, where epsilon is distributed normal 0 sigma squared. So find the maximum likelihood estimate of beta 1 and beta 2 and then interpret the meaning of these two values. Calculate the value of the coefficient of determination, so r squared, and interpret this value as well. Construct a 95% confidence interval for beta 2 and then test our null hypothesis beta 2 is equal to h naught versus the alternative hypothesis for beta 2 not being 0 for alpha is equal to 0.05, and this is our sort of our p value. What is your complete conclusion? So to begin, we have our best value of B2 is, remember that this one is equal to sigma of xi minus x bar yi minus y bar over sum squared of xi and x, this one squared. So naturally, given above, we already have these values, right? We have this one, this value above is equal to 25, and this value below is equal to 30. So then we are already given our answer, which is 5/6. This one approximately equal to 0.833. So that one wasn't too hard. Then we just take B1, which is, as we remember, this one is equal to y bar minus beta 2 of x bar, and if you remember, y bar is equal to sum of yi over n, and x bar is equal to the sum of xi over n. So this one is equal to, let's see here, the sum of yi is equal to 42, and n is equal to 5 minus, let's just take beta 3 of 0.833. And then we have sum of xi, which is 15. And we have sum, and we have n, which is 5. And this one just becomes 5.9. Then to interpret this, we can say that for every x increase, so for every time x, let's see, for every unit that x increases, y increases by 0.833. Remember, this B2 value represents the slope, and we have the intercept. So, and the y-intercept of this is equal to B1, which is equal to 5.9. So in short, we can represent y hat is as 5.9, which is B1, plus 0.833x. So this is the line that will form as a result of our finding our B2 and B1. Next, we have to calculate the coefficient of termination. So if we remember, the formula for the coefficient of termination is r squared equal to regression sum of squares over total sum of squares. So we remember that the total sum of squares is equal to total sum of squares is equal to yi minus y bar squared. This one, as we've seen above, is equal to 32. And then regression sum of squares, remember, is equal to B2 squared times sum of xi minus x bar. Just double check that one. Yeah. Don't have a bracket around it. Okay. So we have this one, which is equal to 0.833 squared times this one we already have determined out from above as 30. So this one is equal to 20.833. So then r squared is, so that means that r squared is equal to 20.833 over 32, which is equal to 0.65. So in short, this means that the regression model explains 65.1% of the variance, the total variance. And everything else remaining. So the 34.9% remaining. So the remaining 34%, the remaining 35% is left as error of some squares. Can be explained by the residuals. So this is considered a, maybe you can also include that this is considered a good fit. This in the case a strong so the fit is considered to be quite good. Okay, so we're not since it's recorded, we might on that one. Okay, so next question is construct a 95% confidence interval for beta 2. So 95% confidence interval for B2. And you have to remember that the expected value of B2 is beta 2. So we're going to say that B2 plus or minus T of 95% confidence interval, since we're working 95% confidence interval, we have that this one is equal to 0.975, and then we have n minus 2 degrees freedom times the square root times the square root of the standard error. And the standard error, if we can remember, is equal to the sample variance over the square root of xi minus x bar squared. So then let's take the SI. So S squared, remember, it's equal to the expected, the error sum of squares over n minus 2, which is the degrees of freedom, since we're fixing two values. So this one, this error sum of squares, if we remember by the formula, is equal to total sum of squares minus regression sum of squares over n minus 2, which is equal to, let's check out the total sum of squares. Total sum of square is what? Nope. So the regression sum of squares is 20.833, and the total sum of squares is 32. So this one is equal to 32 minus 20.833 over n minus 2, which is equal, for n minus 2 is equal to 5. So 5 minus 2, which is equal 3.722. So then we have, so then this one, we already know what this one is. So this one, so let's say, which is equal to 0.833. This is our estimate of B2 plus or minus the T value for this one is 3.182 with, let's see, 3 degrees of freedom. For 3 degrees of freedom is as follows. So this one is equal to square root of 3.722 over 30. This one is equal to, which will result in the following interval of 0.03 and 1.64. So then we have our confidence interval, or 95% confidence interval is as follows. Next, we have to test if whether or not H naught, that beta naught is equal to 0, beta 2 is equal to 0 versus our alternative hypothesis 4, alpha is equal to 0.05. Since this over here and this is identical, we could just use this confidence interval over here. We just use this confidence interval to calculate, to figure out if this hypothesis is rejected or accepted. So in this case, we have beta 2 equals 0. So in this case, our null hypothesis is beta 2 is equal to 0. Since this lies outside of the same confidence, since this lies outside of this confidence region over here, since 0 is less than 0.03, which is the lower end, so we can say that 0 is not inside 0.03 and 1.64, which means that we reject the null hypothesis. So we're in favor of the alternative hypothesis that beta 2 is not equal to 0. So since this, we can say that we reject H naught, and this means that, which also means that there exists some sort of linear, there exists a linear relationship. So there exists some linear relationship between X and Y. Okay, and this one should conclude the STAB57 final review seminar. Good luck on your exam, and thank you for listening.